Yay!
Yay! Hi, everyone. Now let's try to build on the ideas that we've had so far. Okay, here's a more complicated example. Now I've got masses tied together over a pulley, except now one of them is on an inclined plane, and there's friction, right? Here's this little mu down here. So we're going to have to treat friction, and we're going to have tensions and so on. So this is enough. This is enough of a complication to kind of keep us busy. All right, so let's draw in the forces. Let's see what's happening. For M1, it's going to be easy. This is M1G. No problem. And then coming up, I got my tension. And remember from before, that tension, I could write it as T1 because the tension is acting on M1. But I know that we're going over an ideal pulley. So that tension is going to be the same as that tension acting on M2. So I'm just going to call him T. So from now on, I'm taking shortcuts because we've already done it. So that's the same tension. Cool. Okay, M1 is taken care of. I can finish that up. So for M1, I've got that T minus M1G. All right, T's up, M1G is down, and that's going to equal, again, not 0, because this system is going to be accelerating. I put in some masses for M1 and M2. So the masses aren't equal, and the plane is inclined, so maybe this thing is going to slide up or down a little bit. So I better make this M1 times A. Okay, mass times how it's going to accelerate. Cool. Let's look at M2. So from what we did before, I know that M2 has M2G. I got gravity going down. What else? I got the normal force acting always normal to the plane. So normal force is going to be that way. I've got tension going up. Oh, and then I got friction, right? Okay. So here's the problem. I don't know. Let me write down what this problem is. I don't know the frictional force direction. Because ahead of time, I mean, maybe it's obvious to you. It's not maybe to me. As soon as I look at the problem, I don't know what direction M2 is going to go. I don't know if it's sliding down the plane, in which case the friction goes back up because it's opposing the motion, or if M2 is being pulled up the plane, in which case friction would act down, right? I don't know. I don't know which way it's going to go. So, and the main thing is I can't, and we'll see this, I'll try to remember to point this out when we write the equations down. I can't just assume a direction for F because the equations are not the same if I choose F to be positive or negative. I don't have the same equation. So it matters. So what do? Here's the way that I do it. First, solve with no friction. Because what I know is this thing, friction is going to oppose the motion that this thing would have if there were no friction, right? Imagine it's made of ice. And so M2 would start to slide one way or the other, and then friction is going to oppose that. So first I solve it with no friction, and then that'll tell me what direction the friction is going to act, and then I'm going to put it in, and then we're going to solve it. So in some sense, we're solving it twice. The first way a little bit easier, but that's just how I do it. Okay, so with no friction, I've got these forces that are labeled. I've already written M1. How about M2? For M2, I'm going to have an X, and I'm going to have a Y. Okay, for M2, we're going to have our twisted coordinate system. Remember this. We got our X running down the plane for M2 and Y going normal to the plane. This is okay. We can have two independent coordinate systems. One can be weird and the other one can be like regular or whatever. So it's okay. We'll tie them together with the accelerations. So I can assign whatever coordinate system I want to each mass as long as I tie them together at the end, as long as I constrain them right. I'm going to be okay. So in that X direction for M2, What we said was gravity acting down the plane. Here's gravity acting straight down, but I want this, right? I want the component of gravity acting down the plane. What we said last time was that that was our mg sine theta. It's the component of gravity acting down the plane. So that's going in the positive or positive x direction. Let's see. In the negative x direction, I got t, mg sine theta minus t. And that's it, right? So because no friction right now. So this had better be equal to, oops, that's m2, m2a. Okay. Now the y direction for m2, let's see, I got n is going in the y direction, and then I have the other component. I've got this long component of gravity acting down. Here's my angle. So this is going to be, we said mg cosine theta equals 0. It's not accelerating off the plane at all, so that's cool. Okay, so that's going to be it. So we're all set to figure out in where there's no friction, and this is, I mean, you might see a problem like this with no friction. What's the acceleration of the system without friction? Okay, so I have, look at the, with no friction, I don't really need the y equation for m2. That doesn't have an a in it, right? And I want the a. So the a's involve this. I'm going to have m2g sine theta minus t. Okay, t I can get from the m1 equation. T is m1g plus m1a. m1g plus m1a. And this is equal to m2a. By the way, remember how we tied the coordinates together? Let's make sure that the a's are right. Because really this was a1 and really this was like a2, right? Okay, when a1, when mass 1 is pulled up, then mass 2 is pulled down the plane to the right. Both of those are positive directions, we said. So everything is okay. If I just call, and they're the same in magnitude because the rope doesn't stretch, and the directions are okay. When m1 goes in a positive a direction, m2 goes in a positive a direction. So that's okay. I just wanted to check, right? Okay. So now I can solve for, let me just do one more step. m2g sine theta minus m1g minus, I don't know how many times I and lots of others don't distribute that minus sign right, minus m1a equals m2a. Okay, so now I can solve for a. Just bring the a term over, and let me just skip a step or two. So this is going to be m2g sine theta minus m1g divided by, I'm going to have m1 plus m2, right, when you do the algebra. Neat. Okay, let's look at this. Instead of just blindly plugging numbers in, just let's look at individually what they are. Okay, the temptation is, and this is, I do this too. The temptation is to just start plugging numbers in and to get an answer for A. But look at each term. I think there's some value to looking at the terms individually. m2g sine theta, what is that? m2g, that's the force of gravity on m2, right? The weight of m2. It's sort of modulated by this plane, right? I multiply it by sine theta. Well, if theta is 30 degrees, sine of 30 is a half. So the force of gravity down the plane is only half of the normal weight of m2g, is the way to interpret that first term. m2 is 10, right? So this is going to be 50. If you plug in the numbers, that first term is 50 newtons. That's sort of the strength of gravity trying to pull m2 down the plane. It's good when you have these terms, try to interpret each one physically instead of just plugging numbers in. Let's see what each of these means. So here's 50 pulling down the plane. What's m1g? That's the weight of m1, right? That's how hard gravity is pulling the other way, pulling the back up the plane. m2g, that's going to be 60, right? 6 times roughly 10. We're doing g is 10 all the time. So, and m1 plus m2, what is that? That's like, 16 kilograms. So that's just like a total force acting on the system. The total force is the numerator, 50 minus 60, or a minus 10, right? The net force acting on the system is minus 10. And then the mass that the net force is acting on is the masses added together. That's the whole system. And that's like 16. What does that come out to be? 0.625 or something like that, minus 0.625 meters per second squared. Okay, so that's the acceleration of the system. And look, the A is negative, right? I just sort of assumed that A would be positive. But I'm getting a negative answer for A. So what that means is that it really is, in the absence of friction, this mass is going up, M2 is going up the plane. M1 is sort of winning the battle, and so it's pulling M2 up the plane. So this tells me now I can actually solve the problem. Because now I know that my frictional force should actually be like that. Friction is running down the plane. Friction is like red, right? It seems red to me. If I rub my hands together, they get warm, right? That's sort of like red. Or if you slide as kids, you slide on the carpet and it's hot, it hurts, it's red. Okay, anyway, so friction's red. So friction is acting down the plane. That I finally know. Now I can solve the problem. Because now we can put that in. What direction is friction acting in? It's acting in the x direction. So the only modification we have to make, the only thing we do different when we actually solve the problem, nothing changes for M1, right? There's no friction on M1. The only thing that changes is now here, I'm putting a plus F there. I'm adding in friction. That's the only change. I'm adding one term in for M2. All right, so let's see what happens. So we get M2d sine theta minus, the t is going to be the same thing, right? That's not changing. So this is still going to be M1g plus M1a. Now I put in the F. That plus F is equal to M2a. What is F? F is the frictional force. The magnitude of the frictional force is just this mu times n. Maybe you see in the book, the book distinguishes sometimes, whatever book you use, between static and kinetic coefficients of friction. I'm not distinguishing between the two. I'm assuming whatever the way the problem is set up, you're going to know which one it is. Let's suppose it's already sliding, so maybe this is mu kinetic or whatever. Anyway, I just think it looks messy when you keep putting subscripts in. I don't know. It limits understanding when you first start. So for right now, it's just the frictional coefficient. I don't really care if it's static or kinetic. Okay, so it's just mu times the normal force. This is how we get the y equation involved finally. Because what is the normal force? The normal force is this is 2, right? M2g cosine theta. The normal force is M2g cosine theta. So that's how we're going to get this thing involved. So I've got this M2g sine theta minus M1g minus M1a plus, what is F? It's mu times n. That's mu M2g cosine theta equals M2a. Wow, neat. It looks complicated, but we're kind of done. All we have to do is just solve for A. That's kind of it. So we're going to do the same thing we did before. This is going to be M2g sine theta minus M1g. I don't even care to simplify it that much, plus mu M2g cosine theta. And then I'm going to divide by, make that line straight, M1 plus M2. That equals A. So what is my A? When I finally put all these terms in, what do I get? Well, again, let's look at it term by term just for fun. This is like 50. Gravity acting down the plane is like 50 newtons. Pulling back the other direction is 60 newtons, the action of M1. And then, oh, here's my frictional term. What's my frictional term? It's m2g cosine theta times mu. Mu, I said, was 0.1. And if you multiply these numbers out, you get like 8.7. So there's an 8.7 Newton force down the plane that's sort of retarding our motion back up the plane. So if you put all these numbers in, M1 and M2, what you're going to get is that the acceleration is still up the plane. Friction's not going to change the direction of the acceleration. It's just slowing it down, right? So this is a good check. In the end, we better get a smaller number than we got the first time, a smaller magnitude. So A is going to be, what did I get? Minus 0.08 meters per second squared. Thank goodness, because I'm out of room on this page. So this is the answer. We're going to accelerate up the plane at 0.08 meters per second squared with friction. This up here was without friction. Okay, so we took a while with this, but this is a kind of necessarily a two-step problem. We had to solve it without friction just to see which way it's going to go, and that'll tell us what direction friction is. Oh, and I was going to point this out, right? Here's why we had to do it that way. Here's the frictional force, and I put it in with a positive sign because I knew it was going down the plane. That's our positive direction for M2. If it was going the other way, what if I just said, I don't know, I'm just going to guess that it's going up the plane, that the frictional force is going up the plane, M2 is going down the plane. If I make that a minus instead, I'm going to get the wrong answer because that's not an equivalent equation, right? I can't just switch the minus sign on one term. For A, I can switch the minus sign for A because that's switching the minus sign for everything. But for F, I can't just switch the minus sign for F. I get a different equation. So we had to figure out what direction F really is, and then we could solve it and get the right answer. Okay, so yeah, this was maybe a little bit long, but this is a good involved problem that included a lot of different ideas. There's friction, there's an inclined plane, and there's tying two masses, the accelerations of two masses together. So that's a good jumping off point.